started very small. We talked about the individual kind of behavior of an electron, and then we looked at how atoms combine together to make a bond. Then we looked at how those bonded atoms combine to make molecules, molecular structures. That's what we've been focusing on for the last 2 chapters. And now we're going to talk about separate molecules. How do separate molecules interact with each other? So that's what this word intermolecular forces means. Intermolecular forces are attractive forces between molecules and sometimes ions. So not the forces that hold a molecule together, that we call bonds, and that we've been talking about for a couple chapters, but the forces that hold separate molecules together. All right, so these are going to have consequences for things like boiling points, melting points, some other properties that we're going to look at. How tightly molecules can hold each other ends up controlling a lot of the chemistry that we see, because chemistry is ultimately the interaction between substances in different ways. So this is going to have a big influence on that. So what we're going to do first is talk about kind of the basic categories of intermolecular forces, and then we'll see examples of how those manifest themselves, and then we'll kind of bring it out to like the larger bulk effects that we see and how we can use intermolecular forces to explain those. All right, so let's look at the 2 categories of these forces, which the book doesn't exactly split them up into quite, but we're going to do that because I think it makes more sense to think about it this way. So the first thing we're going to look at is nonpolar forces. So all molecules have some way of attracting each other. The most obvious way is what we call the polar or ionic forces, because we know that negative charges and positive charges attract. So that's kind of like, we know ions attract each other. So nonpolar molecules also attract each other. If nonpolar molecules don't have a positive and negative, how could they possibly attract each other? And the answer is through this particular type of force called a dispersion force. This is what the book calls it. They also go under a couple other names, so we might as well list those. They're sometimes known as London forces or van der Waals forces, although sometimes that's a little bit even more general than that, or induced dipole forces. So some other possible names that you may hear depending on the book or whoever's talking about it. We'll try to stick to the term dispersion forces because that's what this book calls them. So dispersion forces work like this. I think it works best if we show a picture. So we'll grab from the book here so we don't have to try to draw fancy stuff. So let's imagine you've got a helium atom. And you can take pictures of it at different times and see where the electrons are. So first of all, what is the problem with that statement, this idea? Is it possible to know where the electrons are in an atom? You're shaking your head. Why not?
Because it's more of like a cloud, like
uncertainty principle says that the product of a particle's uncertainty in position and uncertainty in momentum has to be greater than a certain constant. Remember that equation? So you can only know an electron's position, even if you assume huge uncertainty about the velocity, you can still only know the electron's position to a certain degree. It has to have some uncertainty to it. So, all right, so let's say we have these frames of these electrons. We don't know their velocity, but we're saying that we do know their position. So what you see here is that in the first and second frame, the electrons are roughly, the two electrons from helium are roughly distributed around evenly distributed around the nucleus. But in the third frame, just randomly, because electrons move randomly, those electrons happen to be kind of over on the left side of the atom. Because that would happen, right? Things are moving randomly, occasionally they're going to be on one side. So at the instant that they're on that side, there is a slight dipole in that atom, because electrons are negative. So at that particular instance, there's a little bit of negative on the left and a little bit of positive on the right. Good so far? All right. So that's fine. If that were an isolated atom in the gas state, it wouldn't really mean anything, and the electrons would go on distributing however they go on. But if we have more of a condensed state where the atoms are closer together, like in a liquid or a solid, then something else happens. I'll try to make this a little bit bigger so we can see it better. The neighboring atoms have what we call an induced dipole. So that slight separation of charge that instantaneous dipole causes the other electrons around it to also move. So if that first picture